Good evening, everyone. So, I think we should start our class. So, this week we are going to cover topics from linear programming and P versus NP and reducing algorithm from one to another. We'll look at some problems and look at the solutions. So, I'll also give you some theories that you need to solve the problems. We'll try to basically do this week's problem solving a little faster, so that you guys get some time in the end to ask any specific questions you have regarding the course. So especially if you are going to write the exam on 25th, so if you want any topics covered or any particular problems that you want to discuss, so we'll do that at the end of the session. So we'll just rush through the problems little quick than usual. Okay, so have a look at this problem. This is about using linear programming on a graph, and why it might not be a good idea to do it in certain way. So just look at the four options that we have and choose the correct option. You see the question carefully. It says if you are going to map every path to a variable, then why is it not a good strategy? So if you are solving any problem like let's say finding a minimum spanning tree or those kind of thing, and you're trying to model it using linear programming, so the equations of linear programming are variables that are connected in a linear fashion to each other, and they have constraints over them, and you have to maximize one equation, a linear equation. Okay, so if you are basically modeling it in such a way that each of your variable is a path in a graph, then why will not it be such a good idea to do? That is the question, and you are given four options. It's about cycles, number of paths, direction of the edges, or computation problem. So just choose what might be a correct option in this, and you can, if you have guessed the answer, you can put it in the chat. Anyone wants to attempt the question? Don't worry if you at least one. Okay. Any other people who want to try? We have got Saurabh saying it might be option D. What do others think about that option or other options? Aisha saying it might be option A. Let's see. So let's first just see what linear programming is to get you guys a refresher. So any linear programming problem, it is basically an optimization problem. So you are either minimizing or maximizing a function. Okay, so that is called your objective function, that is shown here. This will be a linear equation, ax plus by form, and you have to solve this equation with some constraints. Okay, and the constraints are again linear in fashion, and they are of the form as in a linear equation less than a constant. Okay, now if you have a graph such as this shown on the slide, and let's say these are the directed graphs, and the edge weights are shown as in the number on the edges, and you have to find let's say the minimum path from S to T. Okay, and this is your problem. Okay, now think about modeling this problem, finding the minimum distance between two nodes, or minimum path. Okay, minimum length path. So if you're modeling this as basically linear programming problem, then your objective function will be what? So the objective function will be minimizing the sum of the weights of the path. Okay, and in this objective function, if you are choosing your variables as your paths in the given graph, so this given graph S to T might have different paths. Okay, and if you choose that as variable, okay, and then what do you think would be a problem with that approach? And think about these options that are given. So you're trying to find minimum path length between two nodes, and for the linear programming objective function, you have chosen each path as this x y variable here. Okay, and you have to minimize over these various paths. Does it make sense first to take these paths as variable? And if it doesn't, then what would be the problem? That is the question. If anybody who has guessed the answer or wants to just justify their option, like why do they think that option should be true? Okay, so Saurav is saying that the number of paths can blow up. Yeah, Pulkit, are you saying something? Okay. Yeah, so the number of paths can blow up exponentially, and if we are choosing the paths itself as a variable, then the whole problem is equivalent to using a brute force algorithm. So basically you have considered all the paths from S to T, and now you are just looking for the minimum value that is present. So in this case you would have to look for all the paths that are there from S to T, and it is a brute force algorithm which will go exponential in time. Okay, let's look at the other options that we had. So we had to be careful to avoid cycle was the first option. So is this really a problem? So if you have a cycle, okay, and you want to avoid it, so what would be, how will that fit into the model of linear programming? What do you do with that such that you do not have any cycles in your solution? So that will come under constraints part. So if let's say here if you have any cycle in this graph itself, okay, so how do you avoid that your solution skips the cycle? Is that you put that as a constraint. So the number of nodes shouldn't repeat basically in the path, and if it doesn't repeat, the cycle will not get formed. So that thing can be handled with linear programming and taking paths as variable. The second option, as we discussed, is a legitimate problem with this approach. Edges may be directed is not really a problem. We can solve. So it really doesn't matter if they are directed or undirected. Depending on the problem or the objective function that we have to minimize, we can model that correctly. Paths can be hard to compute is not really a problem. We already have path finding algorithms. So in the worst case scenarios also, you can really enumerate all the paths. But the whole point is there is no point enumerating all the paths, because this will just blow up exponentially. Okay, so your correct option was B. If you have any doubts about this problem, you can ask now. Okay, Let's move to the second problem. This is quite a simple problem. This all of you should get. So you are given 4 inequalities here, and you are asked like which of them is linear. So you just need to identify the linear equation out of the 4 equations. 4 inequalities. So which one do you think is linear? This everyone should attempt.
B.
Meena, are you saying something? Okay. Yeah, so B is the correct option here. So that is a linear equation. A linear equation is just defined that the variable has only the first degree appearing. So x is your linear equation, x plus y is linear, xy is not linear because you have 2 variables here, and their multiplication will take the degree of the whole thing as 2. So it will not be a linear. Xy you see in equations of ellipses, parabola, circles. So you not even the graphs you can see they are not in linear fashion. So with just linear equations you'll get graphs like lines, planes, etc. With non-linear equations you will get quadratic functions, so it'll be like quadratic curves or circles or hyperbolas, those kind of things. Okay, so to recognize the linear equations in a set of equations, just see that the degree of the variable only appears 1, so it should just be x or y or z or a combination of them, not the multiplications. Okay, fine. Third problem we'll move on to. Okay, have a look at this. So this problem is related to flow networks, and you are given that if you're looking for if you're given the maximum flow of a network, then now you're doing a min cut on this flow network. If you have gone through the material, then in a graph, if every edge is given a capacity of flow, then you can compute a maximum flow from a source to a sink. Okay, and this is your ST flow. S is your source and T will be sink. So this maximum flow that is possible through the network, this is given by capital F here. Now you can basically do a min cut on this graph, which what will that do is separate your source and sink. So there will not be any path possible between source and sink because you have cut the graph such that these two nodes are definitely basically detached. Now you are asked you are given some statements about this min ST cut. So if you have gone through this material, please attempt the question. Otherwise we'll look at the theory part, like how to really solve the question, but just give it a shot and we'll discuss it. Harsh, is there any problem with the audio? Or is anyone else facing that problem? Okay, let me check. Okay. Okay, fine. If it's clear, it's okay. let's look at the theory we need to solve this problem. So the algorithm that this problem concerns with is Ford-Fulkerson algorithm. So you're given, let's say, a graph as shown on the slide, and you have a source A here, and you need to basically send flow out of this A, and you need it to go to the sink G here. So A is your source and G is sink. Flow would be traveling out of A and it will all go to G. So every edge has a number here that you can see. So 0/3 that you see is 3 is the maximum capacity of this edge. So you can only send maximum flow value as 3 here, and 0 I'll explain later as we'll move into the algorithm. It's basically to assign how much flow is actually going to go to this through this edge for the maximum flow case. So whatever would be the maximum flow that can go through this network from A to G. So that flow wouldn't be this maximum values, but there would be some suboptimum values. So that would come under these first number. Okay. Now whatever flow goes out of A, okay, should enter G. Okay. So this equation should be maintained. So the total amount of flow going out of A should equal to flow coming into G. All right. Now if we want to find the maximum flow that can go from A to G, what we simply do is just go through each of the possible paths from A to G. Okay, so what are some of the possible paths from A to G? So let's look at this path. Okay, so it goes from A to D, then D to A, and E to G. Okay, so look at the maximum capacity of the edges of this path. So A to D has the maximum capacity of 3. Okay, D to E has 2, and this E to G here, it only has 1. Okay, so whatever you do, it doesn't matter how much flow is coming from D to E, your edge E to G cannot pass more flow than 1. Okay, so this is the capacity of the edge, so you cannot pass more flow than the capacity. Alright, so if you do choose to send flow from this path A to D, D to E, and E to G, the maximum flow that can go through it is only 1, because the bottleneck is this E to G edge. You cannot send more than 1. Okay, so what you do is you send 1 from E to G, and similarly 1 from D to E and A to D. Okay, so this is represented by these number 1, 3, and 1/2 and 1/1. Okay, so till now basically what you have figured is if you use this path, okay, given path shown in red here, then you can transmit a flow of 1. Okay, and this you have noted in your countdown from this first number in the position. So we have considered this path, and this is the flow that we can basically pass through this path. Now we'll look at some other path. So let's look at this path A to D, D to F, and F to G. Okay, so here you see the capacity as 3, 6, and 9. Alright, and from this 3, the 3 of A to D, we have already taken a flow of 1 to be passed from A to D, D to E, and E to G path, the previous path. So we are already passing flow of 1 from A to D, so only 2 is remaining here. So if you look at previous configuration, we had 1/3, so only 2 is remaining here. So this is called the residual flow. As you're progressing through the algorithm, you are assigning all the path, all the flows that it'll go through that path, and what you're doing is you are basically keeping track of what is the residual flow, what is the remaining capacity of each of the edges. So for example, A to D has a remaining capacity of 2 till this point. So when we move to the next step, we can only pass 2 as the maximum from A to D. So D to F is also 2 out of 6 and 2 out of 9. Alright, so till here, if you guys have any doubts, just these first 2 steps, because we are going to only repeat these steps till we find an optimum solution now. So if you didn't understand, or if you don't know what we are doing here and what the whole problem is, just ask right now. The whole problem is finding the maximum flow that can pass from one source point to the sink node. Okay, and we are considering paths one by one, and we are just assigning the flow that can pass through each of these paths, and we are just keeping a tally of the capacities that are remaining on each of the edges, so we know if we can even use them or not for other paths. Okay, so we move to some other paths now. So just till this point, just notice the capacities that are remaining. So A to D is completely occupied now, so 3 is 3 out of 3, so that means we cannot, it doesn't matter if there are other paths remaining, but we cannot use this edge anymore because this is completely used up. Alright, now D to F and F to G are still remaining, but E to G is completely full now. Okay, we cannot pass any more flow from E to G also. Alright, so let's see at the next path. So this is the next path here. Okay, so in this path, let's see what's the minimum capacity. The minimum capacity comes from the C to D link, so it only has a flow capacity of 1 flow capacity. So from all the other edges also, the maximum flow we can pass is 1. So, and that is what we have done. A to B is marked 1 out of 3, and B to C 1 out of 4, and D to F already was 2 out of 6, if you remember, see from previous configuration, so it becomes 3 out of 6 now. F to G is 2 out of 9 before, becomes 3 out of 9 now. Alright, now let's move to the other path. So this is one more path. Okay, here instead of going from C to D, now we are going from C to E. Okay, and so if you'll again see what is the minimum capacity of this path. So the minimum capacity that remains is 2, I think, or is it 1? It is actually 1. So why is it 1 is, look at this D to E edge. Okay, and this is a point in which you can get confused. So D to E is pointing actually from D to E. Okay, now the path that you see which is marked here is A to B, B to C, C to E, and somehow E to D. Okay, even though the edge goes the other direction, then we have normal path directions D to F and F to G. Okay, now this, so what we have done, now just look at the edge D to E here, which is marked 0 to 2 here. What was it in the previous configuration? It was 1 out of 2. It had a flow capacity of 1 more. Okay, but if we are using any of the edges in the opposite direction, okay, so in the opposite, so if we would be basically pushing flow out of this edge in the direction from D to E, then we would have added up, like 1 out of 2 would become 2 out of 2, because we are the flow would go from D to E, but now the flow would go from E to D, so we are subtracting 1 of the flow, so now it becomes 0 out of 2. Okay, now the capacity of an edge with this algorithm, it can either go to maximum part or it can go to minimum part. So maximum would be the capacity, so like edges A to D, now it is 3 out of 3, so we cannot use it anymore. Now edge D to E has become 0 out of 2, so we cannot use it anymore because it has gone to the minimum 0 number that it can reach, so we cannot use this anymore. Okay, and the other parts we have just added because the flow is in the direction of the edge. And now let's see if we have other paths remaining. So if you'll see, now there are no more paths remaining that you can use because E to G is completely full. Alright, A to D is full, C to D is full, and D to E is completely full. So now there are no more paths remaining that can go to G. Okay, so that means we are on the optimum solution in the algorithm. Okay, if you didn't understand any part or the negative part, anything, ask right now. This is the end of the algorithm. We'll just compute the maximum flow now.
So, but in the videos which you were provided, sir was using reverse edges to calculate the optimal flow.
Yeah, and it is the same thing. Like either you can use that representation, reverse representation, or you can. So the thing is basically the same. So if you are doing the reverse edge, you are basically subtracting out of the numbers. Okay, and so you can whatever representation you feel are comfortable. Okay, it's upon your understanding only. If you understand that well enough, just use it as it is. It gives the same solution.
Okay, sir.
Yeah. Okay. Fine. So now what would be the maximum flow from this graph? Okay, so it becomes So let's see what is the flow going out of A. Okay, so the flow that is going out of A is from A to B, which is 2 out of 3, and A to D, which is 3 out of 3. Okay, and so the total flow is 5. And from G, if you'll see, so you are getting 1 from E to G and 4 from F to G, and it is 5. Okay, and which should be the case. All the flow that is going out of the source should come in the sink basically. And now, so this is the first part of the problem, first theory that you need to know, the algorithm itself. Now where does the min cut comes here? Okay, so if you remember from the slide itself, we had a max flow min cut theorem. Okay, what is max flow min cut theorem? So here you are shown S as a source and T as your sink. Okay, now you have let's say these L and R are your nodes, or basically your set of nodes, you can think. Okay, so now you have path from S to L. Okay, so what in this whole theorem you are doing is you are cutting your graph into two parts. So whatever set of nodes you have, you are dividing into two sets. Okay, and all the edges that are connecting these two sets becomes your min edge set or min cut set. Now why is this cut minimum? Is because the weight of these edges, the sum of the weight is minimum. Okay, and what does the theorem say now is whatever would be the weight, the summation of the weight of these minimum edges, that weight value is actually equal to the max flow that you can get from the network. Okay, so here let's say this one was a network. So let's say we find one cut. It might not be min cut, but let's say we cut like this edge BE, okay, and CE, DE and DF. Okay, then we partition the whole thing into two. So the theorem states that if it would be a min edge set, then the weight would be equal to 5, which is the flow here. Okay, and the weight indeed is 5 here, if you'll see, and this has to be seen in the residual graph. So whatever graph you are getting in the end, so here we have 1 out of 2, 0 out of 2, and 4 out of 6, and 1 and 4 is 5. So the weight of the edges in the residual graph will equal the max flow. Okay, so this is the theorem, and now keeping this in mind, you need another step actually, which is how if I've given you a graph and if I've given you f. So if I've given you the graph that we were looking at and I've given you the number 5, okay, and now you have to basically give me the min cut set. Okay, so the whole problem is how can you give me this min cut set by knowing this number and the graph, and whatever algorithm that you employ, what would be the complexity of that algorithm? So that is the question. So if you want to attempt now, I'll just give you a minute. Just think about all the theories that we have learned about the algorithm and the max flow min cut theorem, and just see what would be one way to find out this min cut.
Can you explain what is min cut exactly?
Yeah, so we have this graph right here. So here you have A as source and G as sink. Okay, so now in this residual graph that you see here, like forget the zero weights, okay, just the residual graph that is remaining. So in that, what you have to do now is basically cut the graph in two parts. So all the nodes that are there, you have to divide it into two sets. Okay, now the edges that will connect these two sets, so let's say if we have cut it like in between here, like as I told you, like CED, like CE and DF we are cutting here. Okay, so this would these edges, if we delete them, the graph becomes disconnected and you do not have any path from source to sink. Okay, now min cut is basically your set of edges which will separate your graph, separate your source and sink, and the summation of their weights would be minimum. So that will be your min cut. Okay, so it's just basically set of edges with minimum weight which will separate the graph into two. That is all. Is that clear? Okay. So that is the whole question. Like, how would you find the edges which will disconnect the graph? If you remember, we have used this kind of language before when we were looking for paths from one node to another node. So whenever we are looking for path and we are trying to find like either the best case paths with minimum length, or just to check if a path even exists or not. So in those cases, we use algorithms for path finding. We look for, especially in these directed graph, we look for check paths one by one. Either we had a couple of algorithms for that, and we basically check if one node is reachable from the other node or not. And in mincut, what you have to basically do is make the source like basically the sink unreachable from the source. So whatever path you find, you have to take edges from those paths, and if you basically take those edges such that their weight is minimum, then that becomes your disconnected graph. Like if you subtract those edges, now those paths are not there, so you cannot reach the sink from the source. So the algorithms that I'm talking about, they are familiar to you. They are BFS and DFS, and that is the solution of this problem. So if you have your residual graph, you basically use BFS algorithm, which will just give you paths from your source to sink. Okay, and whatever paths you have, now in that you pick up the edges. Any edge that you will pick will break that path. Okay, and you have to just break enough number of paths such that there are no more paths remaining between those two. So not the redundant paths. Basically you have to break minimum number of paths such that this becomes disconnected. Essentially what you'll be using is either BFS or DFS algorithm to search between to enumerate basically all the paths from source to sink and just take edges from that. So this will be a polynomial time algorithm. Now there's one caveat that you will not, if you run this algorithm once, BFS, you will not get all the minimum cuts that are possible, because you can have like the symmetric graphs, okay, in which if you run BFS 1, it will give you a certain solution, but if you run it again, it can give you just another solution. Because it's a symmetric graph, it doesn't matter if you cut it here or there, they are both equivalent solution. So in those kind of cases, you might not get all the solutions, but you definitely will get one min-cut solution, and the weight of the edges would be equal to the maximum flow in your network. Okay, fine. So in case you have any questions about this problem, this is a little tricky part that I also found a little tricky. So it's okay if you just take your time, go through the content once again if you find it difficult, but you will get a hang of it, like once you like just get the algorithm set in your head. Okay, fine, we'll move to the next problem. Okay, so this problem is regarding P versus NP part of the lectures, and it's basically also involves reduction of one algorithm on another. So if we have to show that problem B is NP complete, what exactly we would have to show? And SAT, the problem SAT given here, it is NP complete problem. So that means that any problem that can be we'll see like what is the exact reduction, but from the knowledge that you have, if you want to attempt the question, just do it, then we'll look at the theory part of this.
having a checking algorithm a necessary part to be NP complete?
Yeah. So the definition of NP completeness is, so a problem is NP complete if you do not have any basically a solving algorithm in polynomial time. So there are no solving algorithm present in polynomial time, but there is a checking algorithm that is in polynomial time. So what it basically means is that, for example, your Sudoku, the puzzle Sudoku is an NP complete problem. So what that means is, if I give you an incomplete Sudoku puzzle and I tell you to solve it, so you cannot solve it with an algorithm which will be polynomial time in the size of the Sudoku puzzle, which is 9x9 size. And so the solution to the Sudoku puzzle will take non-polynomial time, okay? But if I give you solution to that Sudoku puzzle, I just fill it up myself and tell you to check if the solution is correct or not. Then you can just quickly check every row and just see if all the numbers 1 to 9 are occurring only once, and just the columns, and you'll be done. So that algorithm would just be checking. So maximum it will be O(n) square algorithm, which will be polynomial time. So your NP complete problems can't be solved in polynomial time, but the answer once given can be checked in polynomial time. So you have to have a checking algorithm to basically to claim that a problem is NP complete. Yeah.
Okay, sir.
Okay, let's look at the solution. So first, what is algorithm reduction? Okay, so if I say I'm reducing an algorithm A to B, okay, so what does that mean? So you will have the whole algorithm for A. Let's say take that as a black box. You're giving an input X in this black box and you're getting the right AX output. Okay, so what would you need for it to be reduced to a problem B is basically convert this input X into Y. Okay, so which will be a pre-processing step, and then this Y you put in algorithm for B. So you have made the input which was supposed to go in A, you have made it readable for algorithm B. So that is your pre-processing step, X to Y. Then this Y you are putting in algorithm for B, so whatever is the complexity for B, that will come as BY, and now you have to convert this output BY into AX. So that is one post-processing step. Okay, so now if you want to, so you are given that you have to prove that B is NP complete. Okay, so the first step is to think about what you need to do. Should B be reducible to SAT, or should SAT be reducible to B? So that is the first thing you should ponder upon. So is it B to basically any problem B to SAT, or SAT to B as given in the question? So I'll take up the preparation questions in the end. Let's just finish these questions first, then we'll go for exam preparation. So we'll just run through like last questions like a little bit fast now. Okay, so here the basically correct answer would be from SAT to B. So what you're doing here basically is SAT. Let's say if you're reducing SAT to B, so what you'll have here is SAT would be outside and B is inside. Now you know that SAT is NP complete, so there's no way to solve SAT in polynomial time. Okay, and you know, so if this is the direction, like SAT is reduced to B, then you know if the outer box is NP complete. Okay, so this inner box must have one NP complete block at least. All right. So in this case, you can say that algorithm B is that NP complete block. If you're doing it other way, like if you're proving basically NP like reducing B to SAT, then you do not really know if that reduction itself is the best reduction for like you have reduced made a pre-processing and post-processing blocks, and the whole thing computes more than polynomial time, but you really do not know if there is a more efficient algorithm for B or not. But if you just reduce SAT to B, you say that SAT itself is equivalent to B, then you know that B definitely cannot be solved in your polynomial time, and you also have to give the checking algorithm, which is the other part as I was saying before. Okay, so just go through the last problem, then we'll take up some topics from before. So this is again like P versus NP kind of thing, and it's again a reduction problem, and you have to just check for the option, like just check, give an option, read them, see which of them looks true.
Sir, I've also heard of a term called NP hard. What does
Yeah.
it mean exactly?
So NP hard problem would mean basically that so it's a superset of NP complete problems, and if I remember correctly, NP hard would be like that you cannot even check the solutions in polynomial time. So those would be our NP hard problems. But I can just check this thing. I do not remember on tip of the tongue, but as far as I remember, this was the definition of NP hard. Okay, so here again we are reducing like problem A to B, which is the same scenario as we had here. Okay, and the options that are given is basically if you have so if the best algorithm for A is exponential time. Okay, and let's see if we are reducing A to B here, and if the whole thing solves in basically exponential time, then you know that algorithm B cannot have a polynomial time. Okay, but in other options, if you'll see, if we do not have polynomial time algorithm for A, let's say, then we must also have a polynomial time algorithm for B, which is not true. So if you'll take the other three options, then these things can happen, but may not necessarily be true. But only option 1, if you'll see, if A takes exponential time, then we know that B cannot have a polynomial time. Okay, and because here like one important point is the reduction is given as polynomial time, so you know those steps won't take exponential time, so you definitely know then the middle block has to take exponential time. Okay, so right now we have some time left, so if you guys have any questions regarding the topics or any of the problems that we have seen before, so you can answer right now. Like we can just look at the answers and of any previous problem or any topic not covered.
Sir, I have a doubt from the week 7 assignment.
Okay.
The question was about dynamic programming.
Yeah.
It was about the alignments of the word.
Alignments of the word.
Or two words.
Okay.
Alignments. Like if the characters are dissimilar, then we have to put a tag.
Okay. Okay.
Okay, and so like the DP, it asks like what would be the dimensions of the DP table. So the
Yeah,
answer,
yeah.
correct answer is shown as like the DP table will be n cross n.
Okay.
And like I am saying like we can even have like two columns of n also, because the current value of the column will directly depend on the previous value. Like instead of having a two-dimensional table, we can
Okay.
have two one-dimensional columns to compute the DP.
Okay, let me just pull up. Let me just pull up the question first. Okay, so this is the question, and here we have to find the maximum sequence, like maximum length sequence with incrementing thing, and
Not from the previous week content. I am asking about the
Okay.
assignment which we get to solve.
Okay, fine.
I had asked the same doubt in forum, but nobody had replied.
Okay, fine. So those problems I haven't seen, like I don't like I'll just go through those assignments, so I'll reply you on the discussion forum itself, so others who might have the same problem can get that. So
Yes,
I'll just check.
sure.
I'll just check that question reply. Okay. Any other questions people have? Any topics you want to get covered?
So can you suggest some resources to practice question?
Okay, so what I'll actually suggest is instead of like just practicing the questions, so as many questions as you can get, that is good, like just practice them, but you already have the list of topics that are covered in the course, right? So just make sure, like if you have like a bunch of algorithms, so let's say DFS or BFS, and those you're not too sure about and you want some more practice, so one good way is to just first write the algorithm yourself on a piece of paper. So just like remember the algorithm step by step, such that you can at any time basically recreate that algorithm. So just clarify the steps of the algorithm as much, so that you can just write it on a piece of paper, like just a pseudo code basically. So so the whole examination is just a list of algorithms that you need to know. Okay, and all the questions that you're going to get is just upon some use cases of these algorithms. Okay, so if you just clarify each and every step of the algorithm that you come across, so and you get this clarification anywhere, like from the resources that are covered, like the lecture content itself, videos, or you just go on Wikipedia and just look at the pseudocode, look at the steps, or go on YouTube and just find these algorithms. And the first step is just to create this list of algorithms, write down on a piece of paper what are all the algorithms you need to know to pass the, like to cover the whole course content, and then just clarify each and every algorithm from just, and you'll get a lot of resources just by googling and those kind of things. And even in our course content, like just from the slides, you will get most of the answers, like almost all of them you will get. And even if you do not understand from them, just Google it in YouTube or anything, and just clarify each and every step of the algorithm such that you can recreate it at any time. Okay, and if you have that much grasp on it, then it doesn't matter what use case you have to use that algorithm for in the exam. So it would just be that this is a list of array and use this algorithm on this, and what will be the complexity of those things. So if you know the algorithm correctly, you will be able to just use it on any given input. Only the input will change, right? Like the algorithm is fixed, like there's nobody that can change that algorithm. It's a optimum solution for a given problem. So like my whole suggestion for the exams would just be this, like the whole course content can actually be put on a small piece of, on a good enough piece of paper, such that each block you have as the pseudocode of the algorithm, and just create this piece of paper, just put the blocks of algorithms. Okay, and there'll be like around 20 algorithms. Just put all the 20 algorithms on one piece of paper, and that is it that you need to know. Just before the day of exam, just revise from this, and you will have like the whole course content on your fingertips basically, and that is all you have to do for the exams. Okay.
Okay. Thank you.
Yeah. So Harsh, as I'm saying, like going through all the algorithms won't take so much time. So even if you start right now, you will be able to finish it very comfortably before the exam. And what you have to just do is go look for, just Google each of the algorithm, just write the smallest pseudocode you can on a piece of paper and just keep appending to that paper. And that is the whole preparation that you need. That is all that you need. And if you get additional time, go through the questions, through the tutorial questions or our previous quiz questions, and that is enough material to just revise or just to basically gather some more confidence that you actually know the stuff. But just go through algorithms, write them on a piece of paper and revise. That is all that you need. Yeah. Okay. Fine. Any other topics or questions? This is our last sessions, by the way. So it was okay. All the questions are MCQ type. So the format is exactly the questions that you have gotten in quiz, and it will be exactly the same. So don't worry about anything. You would have to just select the right option. That's all. Yeah, I'm not sure about the number of questions, and like don't worry about what would be the total number of questions and all. Like you will still get enough time to solve all the questions. Like you won't run out of time. Just keep doing at a good pace, and you should be able to complete the paper, in sufficient time. And yeah. But if any other questions, topics you want to cover? So there is no sample paper, especially of the form of that we get in our quizzes and that. So that like Professor Mukund only makes those paper, and I personally do not have any resources for them. Like because most of these computational papers and questions, they are like mathematical proofs and those kind of things, so it will be difficult to find MCQs. But you can like I guess if you really need, you can Google some interview test questions and those kind of things. So many of these CS interviews, they have these kind of MCQs. Some of them you might find, but don't go through a lot of searching and Googling, because that is really not required. You guys already, if you just clarify all the algorithms, you wouldn't need to worry about questions so much. Generally they say you have to practice questions, but in this case I'll just suggest get the clarification about the algorithm, and that will be more than enough to get most of the questions right. So just focus on that. If you have a lot of free time, you have already covered everything, then you can look for online questions, like just Google interview test questions or interview MCQ questions, those kind of things, and you should find some material. Previous year papers, so definitely I'm not sure. I don't think they are released anywhere. I'm not even sure students are allowed to take that home, so I don't think, like I'm not sure you should waste your time on that chase. So I think it'll be better to use your time just to understand what the algorithms are. Okay, fine. Any other questions, queries, doubts?
Yeah, hello.
Yeah.
Yeah, I had a question from this union find data structure. It's not a question, so there could be many variations, right? So we are doing some path compression in one place, we're doing union by rank. So the complexity changes depending upon what you do. So if you don't do union by rank, you get a different complexity if you don't do. So but I'm just confused in one case. What if I don't do a union by rack? That is, I'm not trying to merge them depending on the sizes, but I do a path compression. How does the complexity change there? Is that a good use? Is it a use case for any practical? I mean, any application? Because I think I've read it somewhere, but the complexity is just out of my.
Okay.
It's hard because they use an inverse Ackermann function in this case, right? So when both of them are there.
Yeah.
So with one, it's hard to make out. There is nothing, no resource which says how do I go about.
So there would be. So you're saying path compression in union find, right? Like I'll have to.
Yeah, without a rank. So it's like maybe my tree is very long. It is not a log n height tree. So it's just chain. And if I compress it, then definitely when I compress, all the nodes that are leading to my parent node are going to be split, and I'll get a flat tree.
Okay.
Is that also good? Because we've not discussed that case. I mean, I don't think it's discussed anywhere. It's always they want to make it as, for crystals, we want it to be m log n, right? So we do that.
Yeah, that is
so
why.
That we get
but
it.
I think there would be some use case, especially these, like whenever you get these reverse Ackermann kind of complexity or any of these convoluted functions, the use case is generally very specific for them. So like it would be like something which which goes into which is useful for finding maybe structures in a pattern set, like if you know, like if it is increasing in particular directions and those kind of things. But I can look up for like the use case of path compression, and if I do come up with anything, I'll let you know. But always the use cases would be like little obscure, basically. Like each algorithm of these kinds can, on an average case, they work in these n log n, that kind of complexity. But if you have specific use cases, then you can basically apply these algorithms to reduce it, and that will only work for that particular use case. But anyway, if I find it, I'll let you know on WhatsApp group or discussion forum, and just post it. Yeah. Okay.
Okay, sure. Thank you.
Okay, so there's one question: is there any examples in the DEA book? There might be. I haven't checked that personally, but so it's more of a theory book, and generally these CS theory books are more in line with like proving things or computing complexity. So you would find examples, but they can be overwhelming because it can be too, like they might be asking for too rigorous things. So don't go like reading a book now, like especially in the ending days. Best thing is just to look at the slides, because all the questions would be from your slides, like there would be nothing out of it, and it's the quickest way to revise and understand also. So I would suggest that like avoid any heavy content, like especially now, like just look towards for like smaller, simpler things. What will be the number of questions? I'm not sure about it. I think it is, as Harsh is saying, 40, but I'm not sure about it. Like I don't want to make any claims. But there'll just be enough time to solve the questions, so don't worry about that. So don't worry about too much about the examination pattern per se. Just focus on the theory part, just revise that, and whatever question, whatever pattern will come, you'll be able to answer them. So it doesn't matter, like it doesn't affect your answering ability a lot, or any bit what the pattern is. So just focus on the theory part and just revise as much as you can before the exam, and just you'll be fine. Okay.
I had one question, like this was a basic course on algorithms. Like what if a person is interested to learn more about algorithms? What would you suggest him to do?
Okay. So actually there are many gradients of learning algorithms. So what I would suggest you to do, so this course particularly was about designing and analyzing the algorithms, not implementing them. Okay, so the one the one thing that the course doesn't cover, and it's not intended to cover, like it's the analysis part of the algorithms, but you should definitely either take up some courses which are more implementation oriented. So on NPTEL itself there are more courses which will give you which will make you do more programming and those kind of things. and also basically you can do these programming things on your own also. You don't like need a course or anything to do that. Like what you just need is like just go on these Code Chef and even Kaggle if you're interested in machine learning stuff, and just take up some assignments or some questions there and just start coding. Like the best way to understand algorithms is just by coding them. So if all the algorithms that you have seen, it's a good platform to begin with. Now you know what are various domains in computer science. So now you can go out and go on all any of these like top coders, and there are many online for platforms basically on which you can just code, and you'll get a good basically a reference point for where do you stand with other programmers of your experience and those kind of things. And it's a good way to just keep learning. There are some resources like so there are some resources that are definitely very good. Like you can check out this free code camp. Like I'll just put in some links like that I found useful personally. These are really good resources to learn about coding, any kind of coding. So this is first link, free code camp. So these people are like they have just free tutorials about anything related to programming. So any languages you want to learn, any kind of like system programming, anything you want to do, so you'll probably find a lecture there. They also have a YouTube like YouTube channel on which you can find a lot of content. Okay, and there is one actually at if the best book that I found related to programming was by this guy Donald Knuth. And but these are like these are like considered Bible of programming, and they are very convoluted. So this is not to read just for like just for a course or anything. This you have to read over a lifetime. And also these it comes in like 6 volumes and all that, so it's very big. But it's a really good Donald Knuth basically he's the guy who created latex, and is known for a lot of good research he has done. So this art of computer programming comes in a lot of volumes, and he covers everything with fundamental, like what exactly is a computation itself. Like it starts from very fundamental level. So if you want to just check this out, and over lifetime you can just go through some of part of it. It will give you a good guidance as in what are all the possibilities in computer science. Yeah, but this is what I'll suggest. Like like especially for coding, there are like a lot of resources available for free online. Like even Google has a lot of like free education things. Like if you'll just go on any of the tutorials by Google themselves, they will give you examples to practice that you can code there and then itself. So like if you just want to so, and if you are not familiar with this, so there'll be so if you know about Reddit, so or I don't know if you are active or use it, but they have this programming subreddit, and you can get some resources, or big resource list there. So I'll just share that also. So that is like a very dense list of things that you can go through. That is like an exhaustive resource list. So I'll just put that also there, then wrap up, I guess. Yeah.
What after this class?
Yeah.
Other
Not currently. Like I might come. I'm not too sure. Like, but at least not this semester. I think next semester, I might come. Yeah.
actually, there are sessions going on for gate preparation.
Yeah. You're telling me about that. Yeah. But I'll see.
Is
Actually,
there any
like I think.
you're going to find out?
I think for all the session they might already have assigned one of the TAs, but if they have anything ongoing, I might come back, but not too sure about that. Like that is really not up to me to
I
decide.
just
Like
want to
if
know, I mean, there would be a limit that, like, as a TM fellow, you will be limited to, how many assignments how many
Yeah.
sessions you can have
Yeah.
in a particular.
Yeah.
So are you done with those limits? I mean, your limits, or is there still
No,
chances that
so
you?
yeah, like we have to do actually just one course per semester. So that's why I was saying that if I come, mostly I might come in next semester. But we'll see. Like if they have an opportunity or they are looking for TAs, well, yeah,
Because there,
maybe we can.
for computer science, there is only single TA available for gate preparation. But in other branches, there are multiple TAs available.
Yeah.
So there is a lack of TAs. So I just want to know whether possible
Yeah.
for you.
Yeah. But I'll see, like if they give me an opportunity, I'll surely come. Yeah. But otherwise, you'll still have enough TAs. If you are having a problem with number of TAs, then you should definitely inform the TA of that gate session and tell him that you require additional sessions, and they might be able to talk to the NPTEL people.
Yeah. I mean, I requested him that he's from IIT Mumbai. Of a PM fellow who says that currently we have only lack of TAs for computer science specifically.
Okay.
Or other branches, there are at least 5 to 6 TAs available.
Okay, fine. So, yeah, if that is the case, they do call us, like if they are looking for additional TA, like I will be there. Yeah. Let's see how it goes. Like when do they, like even if they, like I'm not even sure if they'll even do the assignment now this semester, because like it happens like once per semester only. So I think only next semester they will be doing a fresh set of assignments. Yeah.
Okay.
Yeah. Okay. Fine. Do you guys have any other questions? Queries? Okay, so this was my last session for
This
today.
this is last section, and I'm also preparing for the gate examination. Is there any possibility that I can ask you by mail or something, like 15 or 20 days, any query or confusion if I have?
Yeah,
I mean, if you have time.
Yeah, you can ask me, but it is really dependent on like the time I have. Like actually, I'm also a PhD student, so I'm doing my research work here, and I barely yeah. But yeah, surely I'd like to help you guys. Like it was really fun to interact with all of you. If in future also you need anything, like you can hit me up. You know my WhatsApp number. Like as much time as I'll have, I'll try to give from my side.
Can you share any contact information?
Yeah, so if you are there on the WhatsApp group, like you can find my number there. Are you?
I'm not there.
Okay, so on discussion forum, basically you'll find a post by me which is useful links, and that you'll find a link for WhatsApp group, so you can join that, and you can find my number there. Yeah, okay, someone has put that in the chat.
Thanks.
Okay, fine. Okay, so I guess we'll wrap up here. It was fun to teach you guys, and I had a good time. I hope you learned a good deal from this course. And don't stop learning. This is just one of the many courses that you'll do for programming. It's a very interesting field, and like you'll be really glad to learn so much about all these things in future. So never stop learning. Like that is, and through anything, like this NPTEL is just one platform, but you have, like, if you are just willing to learn, there are like thousands and millions of resources outside. So just keep that curiosity going on, and like you'll find the right teachers and right resources. Yeah, and keep in touch. It was fun to know you. I know a lot of you guys by name. It was fun. So yeah, I hope we'll maybe meet again sometime. Yeah. Okay. Fine. Bye guys.